In this tutorial, we'll be doing an example on topology optimization with Nastran. This one's very different from the other ones because we're taking into account stress constraints. And this is our goal. We are going to take this object that you see on the left. We're going to use topology optimization to come to a solution that looks sort of what you see here on the right. Our goal is to minimize the mass, while at the same time making sure that our stress and displacements are within the constraints that we define. So in this tutorial, I will get you up to step number 2. After step 2, there's this process of smoothing out your mesh and fine-tuning your final part. I'm leaving this up to you. Again, I'm getting you from step 1 to step 2. So what are we covering today? I'm going to quickly cover the optimization problem statement. This is a summary of all the design variables, if you will, the objective and the constraints. I'll perform the optimization in Nastran, and then towards the end, we'll look at the results. One other thing we will be covering, and I'm holding off on this until the very end, there's some commonly asked questions regarding topology optimization. I will cover these towards the end of the presentation after our initial tutorial. So let's go ahead and jump into it. If you are a professional engineer and would like more training or personal training, you can contact me at this email address and I will definitely get back to you. If you're a student or professional engineer and would like access to the Nastran Solution 200 web app, you can also send me an email with your request and I will definitely grant you access. Now, let's quickly talk about how the model's configured. 2 of the holes are constrained. On the third hole, we actually have a load applied. We actually have 2 load cases for this example, so we'll be optimizing for 2 load cases. Now here's a quick snapshot of what the problem statement is. We are going to let the entire part vary. At the same time, we're going to impose our stress constraint on the variable, or the design region, I should say. Here we are saying that the maximum allowable stress would be no more than 200 megapascals. As for the objective, we want to minimize what's called the fractional mass. We want to minimize this as much as possible. If you have a question regarding what fractional mass is, I cover that towards the end of the video, so stick around for that. As for our design constraints, in addition to the stress constraints, we are imposing a constraint at this hole. We are making sure that node 5622 does not displace in the z direction more than 0.0008 meters. Now let's go ahead and talk about what the procedure is to set up topology optimization. The first thing you have to have is a BDF file. I am working on the assumption that you've already gone ahead and successfully performed a stress analysis in your pre-post processor. Everything works until this point. On your desktop, you would have your BDF file or DAT file that you wrote out from your pre-post processor. Alternatively, in the video description below, you'll find a link to this BDF file. You can download it and follow along. Now, what happens after you have this BDF file? You then have to convert it to Nastran Solution 200. Today, we'll be using the Nastran Solution 200 web app. This is going to let us set up the model and convert it to Solution 200. We can specify the design region, the variables, or rather the design region, the objective, and the constraints. So let's go ahead and go through the steps that are needed to perform this conversion. The first thing you want to do is navigate to the web app. So let's go ahead and go there now. After you navigate here, make sure you are in the topology optimization part of the web app. So here, if you look at the name, it says topology here in the top left-hand corner. Once you're here, let's go ahead and upload our BDF file. Here, the web app will identify regions that can be set as variables, if you will. Here, I want to set the P solid 1 as a design region. And here, if I look at the problem statement, this entire part, if you will, is associated with P-solid 1. So let's go ahead and select P-solid 1 as the design region. Now, if you want to apply a stress constraint, here under options, turn on or mark this checkbox called show stress limit column. This is where you can type in your upper limit. So I think the value was 2E8. So here, let's go ahead and type in that correctly. Let me double check here and make sure that's correct. Now let's go ahead and talk about our objective. By default, the web app will create an objective to minimize compliance. This is done automatically. In this case, we don't want to minimize compliance. We actually want to minimize the fractional mass. So let's go ahead and select that by clicking on the plus icon. Here we have our new objective, FR mass. Now for the constraints, we are dealing with a displacement constraint. So here, let's go ahead and first delete this existing constraint. Here by default, the web app will automatically generate this first constraint for you. Let's go ahead and delete that. And let's go ahead and add a displacement constraint. We'll constrain this displacement in the Z or third component. And this is happening for node 5622. So let's go ahead and type in 5622. And then I believe the upper limit will be 0.008. So let's go ahead and type that in. Now, once you've done this, you can then move on to the exporter. So let's go ahead and move there now. And you'll notice that there are two download buttons there. This will download local copies of these converted BDF files. The first BDF file is the same BDF file that you have on your desktop, with the exception that it's been converted to solution 200, as you can see here in the top left hand corner. Also, you'll see that there are some statements for the optimization, such as the design objective and the design constraints. So the second file has all the Nastran entries you need for the design region, the objective, and your design constraints. So again, what the web app has gone and done, it's converted the file to solution 200. It's allowed us to go ahead and define our objective, constraints, and design region. Now, after you do this, feel free to start Nastran, select the model BDF file, and perform the optimization. And one thing I forgot to do, let's go ahead and cancel this optimization. Well, here I think it may have finished, so let me check that. Oh no, it has not. This optimization will take more than 50 design cycles. So here, back in the web app, go to settings and increase the maximum number of design cycles to 100. And then let's go ahead and re-download these files. And then this optimization will take a few moments. So let's go ahead and run the optimization. You know, while this optimization is happening, it might be worth covering those frequently asked questions I mentioned a moment ago. So let's go ahead and talk about the first question. What is fractional mass? So fractional mass is basically the amount of mass that has been retained during the optimization. So here, if we consider this entire rectangle here, this is the original mass. Now, if the fractional mass is 0.75, that means up to 75% of the mass has been retained. Now, if the fractional mass is 0.5, that means that half of the mass has been retained. Typically, when you see a topology optimization, the goal is to minimize the fractional mass as much as possible. One other thing too, if you're ever typing in a fractional mass, make sure you always use a value less than 1. The last thing you want to do is type in a fractional mass of 2.0, which would mean that you've retained 200% of the mass. That might actually cause an error within Nastran. The other common question is, what are the design variables in topology optimization? One thing you'll find out when you perform your optimization, Nastran is not deleting and adding elements. What happens instead, each element is assigned what's called a normalized material density. Think of the normalized material density as sort of a scale of importance. So here on the far right, you see the spectrum. If you see any element with the normalized density value of 1, that means that that element is very critical to this part when it's loaded. So this is, if you see any element close to 1, that means that element should be capped. Elements that are very close to 0, and any elements that are close to 0, these elements are not as important and could be potentially removed from the part. So here, just to give you an example of what a normalized material density would look like, let's suppose that the original density of the whole part is 4,000 units of density. So here I'm writing 4,000. So now what happens when when the design variables are created? So here, let's go ahead and pick an arbitrary element. The normalized density might be 0.5 as an example. Let's suppose the normalized density is 0.5. That means that the element here has a reduced density of 2,000. So here, if I write down 2,000 and divide it by 4,000, I get the normalized density of 0.5. So now each element will get its own density. So here, imagine there's a density I for element I. This is what Nastran does. It gives each element its own normalized density, and it increases or decreases the density just to gauge how important the element is to the rest of the part. Here on this slide, I have a plot. I'm using a bunch of spheres to represent the size of the normalized density. Here you can see that the spheres can range in size. They could be really large or really small. When they're really small, again, that means that element has very little impact on the structure, and that piece of material, if you will, can most likely be disregarded. Now, in a moment, I will go ahead and show you how to display which elements are very critical for the design. And here we'll go ahead and see if the optimization has completed. So the optimization has completed. Let's go ahead and look at the very end of the file. And let's go ahead and make sure we have this message here that says, run terminated due to hard convergence. This is indication that the optimization has gone through successfully. So now let's go ahead and look at the results here in our pre-post processor. Under tools, if you go to design study and click post process, you can select a des file, DES. This des file is created during the optimization process. So let's go ahead and select that file. And it would be under downloads. Here, let's go ahead and click apply. So now this file contains all the new optimized normalized densities for this part. So here, let's go back to design study post process. Let's go ahead and click on display results. And here I'll type in a threshold of 0.3. What this is saying is keep only the elements with a normalized density higher than 0.3. So let's go ahead and plot what that looks like. And make sure you select this row here. And there we go. So here we have a plot of elements that have a normalized density greater than 0.3. And here, if I wanted to, I can also just make a plot. So here, let's see if we can do that real quick. And let me see. Maybe I'll show everything greater than 0.01. So let's go ahead and click apply. So here's another view showing us with the fringe rather what the range of normalized densities are for each element here. Again, if you see anything that's close to 0, so here are the white elements, that's a very non-critical element. Anything close to 1 means that it's very critical to the design. Now, I've already gone ahead and taken time to smooth out the part. So let's go ahead and jump to that. And let's review what the stress state of that new part is. I'm doing this just because it is, how do you call it? You always want to make sure that the optimization has honored your design constraints. So that's what I'm confirming right now. Let me import, again, the version that's been cleaned up a little. So here's the cleaned up version of the model. I've already taken time before this video or tutorial to go ahead and clean it up a little. Now let's go ahead and look at the stress results from this new version of the model. And give me a moment while I go ahead and locate the result file. And let's go ahead and look at our stress contours. Let's go ahead and show von Mises stress. Let's turn off element averaging. Let's go ahead and plot this. Here we can see that our maximum stress is well below the upper limit of 200 megapascals. And this is for load case 1. Let's go ahead and look at load case 2. So here you can see that our maximum stress for the second load case is about 150 megapascals, which is underneath the upper bound of the stress constraint we defined a moment ago. And the other thing we should definitely check, I don't know if I'll be able to show that. I should be able to. We wanted to make sure that the displacement at this node on the right was no more than 0.0008 meters. So let's go ahead and see if we can inspect that displacement just to make sure it's has not exceeded our limit. So let's go ahead and see what that is. So here we get a value of 3.48 times 10 to negative 5 in the z direction. So that looks good. And let's look at the first load case now. Here we get 0.000836. Now there will be some slight violation, and let me double check and make sure that was the constraint we had here. Right, 0.008. So there will be a slight violation of the constraint, and that is okay because there are tolerances that are used during the optimization. And again, that is a tolerance. You can make the tolerance a little more strict so it's within the constraint. Alternatively, what you can do is say, instead of 0.008, you could say 0.00079. So you are definitely underneath that the limit. So this is an alternative method if you really have to be underneath 0.008. So there you have it. Let's go ahead and see if there's anything else to discuss. I believe that was everything I wanted to cover. Again, if you're an engineer and you're interested in performing topology optimization and you want to get started, feel free to send me an email at this email address and I would definitely get back to you. If you would like access to the Nastran Solution 200 web app, you can also contact me at this email address. There have been a number of students who have approached me. I definitely have been there to help them. If you're a professional engineer, you can also get free access to the web app. With that, that's the end of the tutorial, and thank you for watching.